Everyone, am I audible? Can anyone confirm? Hello. Yeah, hi. Vakar, am I audible?
Hello? Yeah, Vedantu, you are.
Oh,
Sorry, Vedantu.
Vedant. Yes, sorry. So, hi everyone. Welcome to the solution webinar for Code Kaze. As you guys were the part, so you guys have attended the test, the competition that. Hi everyone. Am I audible? Sorry. So as you guys have already attended the Code Kaze competition on 15th of November, so this is the solution class for the contest, and Vakar will be digging through the solution here. Vakar, you can start the solution webinar.
Okay, just give me a second. Okay, so let's get started with this. Let me share my screen real quick. Sorry, Vedanku, sorry, my bad. Can you enable screen sharing?
Hold on, I just do that.
Yes.
Just check. Is it you're able to?
Yeah, now I am. Oh, thanks. Hi, everyone, and this is Vakar Ahmed. So I welcome all of you to this webinar for editorials for Code Kaze contest problems. And thank you, Vedanku, for the introduction. So as far as my introduction is concerned, as I told you, I am Vakar Ahmed, and I have been doing competitive programming for like 5 years straight. Vedanku, am I audible?
Yes, you're audible.
Okay, so if noise coming from background, I can take a pause for like 2 minutes. Or is this okay?
You're clearly audible. There's no disturbance
Okay,
in the background.
sure. Thanks for confirmation. So I've been doing competitive programming for like 5 years and have been teaching it for like approximately for 4 years. So I've been assigned the work to take you through this editorial webinar. So since we are bounded by the time, we unfortunately I can't cover all of the problems that appeared in Code Kaze contest. So I have taken some of the problem that we can cover in 2-hour window. Okay, so I'll be taking you through these problems one by one, and we'll be discussing not just the solution, but how the thought process goes when you are going to construct the problem. When you read the problem, what is the thought process? Okay, so let's get started with the very first problem. So I've chosen some problems. I'll be taking you through these problems one by one. So let's start with the first problem. I cannot increase the font size. Okay, so here is the problem. So uh, Coding Ninjas is organizing a 10-day long hackathon in which students from all over the world are participating. Okay. In order to accommodate such a massive amount of students, they have they have rented an apartments. Okay. So now we have an apartments and which are numbered from 1 to n. Okay. Each apartment consists of a number of rooms. So we'll be given an array of size n, right? Because we have n apartments. And the room in the ith apartment are numbered from 1 to ai. Makes sense. So let's say the first apartment is having size like 5. So the rooms will be numbered 1, 2, 3, 4, 5, right? Makes sense. Now, in order to combat cheating, mobile phones are strictly prohibited in the area, and to welcome the winners of the last hackathon, letters are being sent out to them. Okay, instead of mobile phones, we are using letters. However, the managers forget to add the specific apartment number and the specific room number on the letter, right? So they are sending the letter, but they forget to add the apartment number and the room number. Assume that the rooms are numbered from 1 to A1 plus A2 plus A3 dash 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 to AN. So basically, let me explain this with an example. Suppose I had like 3 apartments first apartment is having size, let's say 3. Second apartment is having size, let's say uh, of 5, and the third apartment is having size 2. So the total number of rooms we have is 8 and 2, 10. Okay. So what managers did, they wrote down only a number, which is a room number. Okay. So we have rooms, we have 10 rooms, right? So they put a number from 1 to 10, right? And they forgot to mention which apartment and which room number. Now, for each of the M letters, determine the particular apartment and the room number in which the apartment were in the apartment where the letter must be delivered. So it's our task, given the room number, right, in the range 1 to some of the AIs, right? We have to determine which apartment does this letter belong to, not just apartment, also the room number, right? So now the question must be clear, right? NNM can be as large as 2 into 10 to the power 5. AIs can be up to 10 to the power 9. And of course, the BIs, which will be given as the input. Basically, let me explain this sample test case. So you'll be given N and M, and the number of apartments you already know. M will be number of queries or number of letters, right? After that, you'll be given AI array, right? A array, I can say that. So this represents size of each apartment. Now, after that, you will have M input, and in which basically each time you'll be given a room number. Basically, you have M queries. Each time you are given a room number, and you have to tell which apartment and which room does it belong to, right? So output will be for each test case, apartment number and the room number. So now that the question is quite clear, let's let's see how we'll solve this problem. Okay, so let's go back to the whiteboard and let's see how the solution goes. Yeah. So let's solve the problem with an example. So let's say number of apartment, or let's take some other number, let's say 5. Okay, I have 5 apartments and array A is given like this. Size of the first apartment is, let's say 3, then 2, then 4, 2 and 1. Okay, now to solve the problem, what you can do, see let's see how many rooms do we have. So the input will be in that range from 1 to 9, 10, 12. So 12 rooms we have in total, right? If someone says hey, BI, let's say ith query says that, hey, send this letter to the 8th room. So 8th room, you see, this is like 5 and 4, 9. 8th room lies here, right? In this apartment, because at this point you have only got 5 rooms, and here the rest of the 4 rooms are there. I mean, if you take this apartment, the sum goes over 8, right? So your 8th room must be here. Now the question is, so of course you have found the apartment number, which is third apartment, and which room is that? Till now you have found 5. So the first room of this apartment is till now we have found 5. Now we need 3 more rooms. So first, second and third room of this apartment will be the 8th overall room, right? So 3 and 3, third apartment and third room. Now how will you find this? To find this, what you can do, you can construct another array, in fact 2 arrays, okay, where you can construct. Let me just strike this down, where you have my handwriting, start, okay, and the end. So here for each apartment, we are going to store the starting room number and the ending room number. Okay. For first apartment, starting room number is 1 and the ending room number is 3, right? For the second, it is actually 4th room, right? Because first 3 rooms are here. Now the 4th and 5th room are here, right? So starting is 4, ending is 5. Then for I think starting from 6 room number till 9 are here, and then my bad, Just a second. So starting from this, we have covered this one also, right? So 6 to 9 are here for the third apartment, and the for fourth apartment we have starting from 10. We have two rooms, so 10 and 11. Ending will be 11, and finally the last one starting from 12, ending at 12. So now we have starting array and the ending array, right? This we can construct in linear time. After that, if you see, the start and the end, both of the array are actually increasing order, in increasing order, right? And hence this is actually monotonic, right? This you can, if you map it, it will form a monotonic function. And when you find a monotonic function, that means you can apply binary search here, right? So when you are trying to solve a problem, and you to solve a problem, you can construct a function, right, in which you are able to construct a function which is monotonic, either increasing or decreasing, or non-increasing or non-decreasing. Then you can apply binary search there, right? So how will you apply binary search here? Let's go back to here. Let's say I wanted to find 11th room. Okay, room number, not just 11. Let's say I wanted to find, my query says find out apartment number and the room number of fifth room. How you're going to solve this? Of course, apply binary search. And how? See how many apartments we have. We have n apartment. So of course, my answer will be in the range 1 to n is 5. So either my answer will be, my room will be in the first apartment, or basically room will be in this range, right? Now, to apply binary search, what you will do, of course, you will calculate mid. In this case, this will be 3, and check whether third apartment is the right apartment. And how can you confirm that? See, if this room lies in the third apartment, then uh, this value bi, let's call this bi, right? Bi must be greater than equals to 6 and less than equals to 9, because we have already calculated start and end. So this room, that 5, must be in this range, right? This range rooms are present in the third apartment. So you will check whether the bi is in this range. The answer is no. So third apartment is not our answer, right? That means we have to shift either to our left or to our side, what we do in binary search, right? So what we'll do, we'll check, should I move to the left or to the right? For that, you can compare your bi to either start or end time, doesn't matter. See, check if bi is actually greater than 6, which is start time. We will compare with start time. So is 5 greater than 6? The answer is no. That means this apartment must lie on the left hand side, right? In the range L, which was already there, to this was mid minus 1, right? So you can set your R to mid minus 1, which is going to be 2. Oh, my bad. This one, right? Now my search range is only this. Again, you will calculate mid. Mid is equals to 1 plus 2, that is 3. 3 divided by 2 is 1. So now I'll check whether the first apartment is my answer. The answer is no, because 5 does not lie in this range. So first is not my answer. I'll again check whether 5 is smaller than 1. The answer is no, 5 is not smaller than 1. That means my answer lies on the right hand side. So what I'll do, I'll update my L. L will become mid plus 1, that is 2. Again, I'll calculate mid. Mid will become 2 plus 2 divided by 2, that is 4 by 2, that is 2. I'll check whether second apartment is my answer. So if second apartment is the answer, then bi must be in this range, which is true, and hence you have found your answer. That means mid represents your apartment number. So you can print apartment number as 2. After that, you have to print the room number. How you can do that? See, it starts from 6. Oh, sorry, it starts from 4. So the first room, so 4 represents first room, 5 represents second room, right? And we are searching for room number 5, which is second room of the second apartment. So you can print 2. And how programmatically you can find this? All you have to do is this, bi minus start of the apartment which you have found, which is mid, okay, plus 1. So basically 5, oh sorry, 5, bi is 5, 5 minus starting is 4 plus 1, right? So basically 2. So this way you have found this also, right? So now you got the idea that how you are going to solve this problem. So to solve these kind of problems, again, when you are able to construct monotonic function, your mind should always go and find a solution using binary search. You have a monotonic function, you can apply binary search, and that's how you identify that the given problem can be solved using binary search. Okay. Now, so if I can give you any hint for a better programming or competitive programming career, along with this, that will be that learn as many algorithms or data structure that is possible. Okay, because competitive programming is basically it tests you whether you are able to construct a solution or not. For that, of course, you have to apply certain algorithm or data structure, because these are designed, each algorithm or a data structure is designed to solve a particular type of problem, right? It is possible that a certain problem can be solved in many other ways. Yeah, that is possible. But still, uh, if you have no idea about an algorithm which can be utilized to solve the current problem that you are going to solve, how you're going to solve it, right? So for that, just learn as many algorithms and data structure that is possible, right? So yeah, this is how you're going to solve the first problem. Now let's go back and see what was the second problem. So let's stop share. Let's go back to so now we have solved this problem, right? Now let's see what the second problem says. The first problem was of 40 marks, and same goes for the second problem. This is also of 40 marks. So let's have a look at this problem first. So the question says this: a ninja loves to spend time with his nature. Sorry, a ninja loves to spend time with nature, and he's been participating in Ninja Scouts for 3 years in a row. Okay, his team completes all the given tasks with perfection, and this year too, they are planning to win. Okay, great. But not everyone in the camp is a fan of their team. I see. So Nathan and his team have decided to win this time at any cost. They come up with a plan of changing Ninja's registration number X. Okay, so Ninjas have registration number X to disqualify him, as he's the most valuable player on his team. Okay, so they develop a function G that maps every digit from range 1 to n to some other digit. Okay, there is a mapping which is provided by G, function G. So each number in the range 1 to 9 is mapped to certain other number, right? It can be same also, like 1 can be mapped to 1, that is possible. Now they change all the digits of a non-empty contiguous subsegment according to the function. So what they do, that Ninja has registration number X, they want to change it, right? To change it, they are going to use function G first, right? Mapping function G. And the second thing is they are only taking a subsegment which is contiguous, basically subarray, right? And they are going to change all of the character using G function, right? And again, they're going to change a subarray of X only. Now, for example, they also explain this with an example. So if X was 2, 3, 4, 5, G3 is 5, G4 is 8, G5 is 7, they can choose a subsegment consisting of last 3 digits. So basically, they are changing this subarray, right? So 3 will be mapped to 5. So you see, at the place of 3, we have 5. 4 will be mapped to 8, and then 5 will be mapped to 7. So the new number will be 2587. So you understand the problem statement, right? Now, can you help Nathan and his team choose the maximum possible number by applying this operation no more than once? So they can't apply the operation more than once, right? They can apply it zero number of times. That is possible. It doesn't say exactly once, right? So what information do you have? Basically, you have to convert X into as maximum number as possible. For that, you can do one operation exactly. At max one number of time, right? And that is choose a subarray of X and map all the digits in that subarray using function G, right? And try to maximize the X, right? Let's take a look at this example and try to understand this. See, So I have like 1 7, let's just, yeah, 1 7 and then 3 3. This is your input number X. So you'll be given n first, right, in the input, then n digit number, so 4-digit number. After that you'll have 9 numbers, okay, 9 integers that basically represent your mapping. 1 will be mapped to 1, 2 will be mapped to 2, 3 will be mapped to 5, uh, 4 will be mapped to 4, 6 will be mapped to, sorry, this is 5 will be mapped to 6, and so on and so forth, right? So this is the input, and we have also the mapping, right? So what they have done, they've chosen, I guess, this subarray and changed every element. So 1 will be 1 because we have not changed it, right? So 1 will be 1. 7 will be mapped to, sorry, they have not changed 7 also. Only the last two elements they have changed, right? So 3 is mapped to 5, so they have converted this and this to 5. So basically, they have taken this subarray and perform the mapping, right? The last two digits only. And this is the maximum number that you can get, right? If you convert 1, it will be converted to 1 only. So there's no change, right? And for 7, 1, 2, 3, 4, 5, 6, and 7. 7 is being converted to 3. There is no point changing a bigger number to a smaller number, right? So that's why we have not gone with that. We have only taken the last two digits and converted into a bigger number, right? So now let's see how we can solve this problem. Let's construct our solution. So let's stop this here. And let's start our whiteboard. Okay, I need an extra page. Here, let's start with the fresh one. So again, I have certain digits like 2, 3, 1, 5, 4, right? Now, since first important observation you should make is this: you can change at max one subarray, right? Not more than that. So if my mapping was given in such a way that I can transform one, let's say 5 to, I'm using too many different characters, so it will take time. So let me just take 3, 2. Okay. So if the mapping was given something like this, map 1 to, let's say 1 only, map 2 to, let's say 2 only, or let's reduce. Okay. And map 3, let me change this to 1. Sorry. Okay. So this is 1, 3, 1, 3, 2. Okay. And 2, let's change it to 5, right? And 3, mapping of 3, let's do it to 4, right? Now here you see changing, we can change 1 to 1, so it doesn't make any difference if you change 1 or not, right? Now, but you can change 3 to 4. That means it's better if I change 3 to 4, right? So let's change it, right? If I want to change the second one also, I have to go for the whole subarray, right? That means I'm forced to do this, right? So 1 is already being changed to 1, so nothing changes there for 1, 4. Now the question is, should I change this also? The answer is no. Of course, this is being changed to 5, right? So we'll leave this as it is. So we have changed this subarray. Now let's see why should we change it, right? For any specific, first of all, we have to decide what is the size of the subarray that we want to change, and from where it should start, right? Starting position. So for that, if you take any number, let's say, right? If you are able to change any number which is appearing as early as possible from left to right, you should do that, right? For example, if there was an option to change 7 to something bigger like 8, 9, 8 or 9, right? We don't have 0 or 10. If there was an option to change 7 to something bigger like 8 or 9, you should do it, even if this is the only character you can change. Like for the rest of them, all of them are being converted to 1. This is the only, g of every other is only 1. G of 7 is equals to 9, let's say. So if you want, let's make them bigger. All the other numbers are being converted to 7, and 7 is being converted to 9, right? So even if you are able to change only this character, you should go for this. Why? Because see, uh, if you change this character to 9 and you are not going to change anyone else, let's, right? If even if you keep all of them as it is, and in other situation, you kept the first one as it is and converted all of the rest to 9. Let's say this one still be bigger than this one, right? When you're going to create a bigger number, maximum number, or lexicographically smaller, bigger number, what you should do when you're traversing from left to right, the first number holds the highest weight. Okay, the first number is having the highest weight, then this number, then this number, then this number. So if you want to create something biggest, you should try to change the first number, right? If you can, right? So if we take back the example, we had like, I can't go back to the example. So let's create our own, right? So let's go back to new slide. And let's say I only had like 2, 1, 5, 1, 3. Okay. So let me define the function also. G of 1 is equals to 5. G of 2 is equals to, let's say 1. G of 3 is equals to, let's say 5 again. G of 1 I have already defined. Which one is left? G of 5. G of 5. G of 5, let's G of 5. No, this one should be like 4. Okay, so this is the mapping. So what you will do, since we know that the traversing from left to right, the first one that you can change, you must, because from left to right, when you go, each digit is having higher weight than the other ones towards the right of it, right? So can I change 2? The answer is no, because it is being reduced. So I should not do it, right? Can I change 1? If you see, 1 is being mapped to 5. So you must do it, right? This is the subarray that starts. This is where your subarray starts, right? So 1 is mapped to 5. Now, should I change the next one? This is the point where your subarray starts, and you are going to change as many elements as possible starting from this point, right? Now, can I change 5? 5 is being changed to 4, so I should not. This is the only place I can change, right? And I should stop here. So 5 won't be transformed into 4. So I cannot transform 5 to anything. So I leave 5 as it is. Now, since I have already converted one subarray, I am not allowed to convert other subarrays, right? Otherwise, I could have converted this to 5 also, but that will create a problem. So I leave 1 to 1, 3 to 3, right? So this is the only subarray that you have to change. So what you have to do, first of all, find the first place which can be converted. Just traverse this number from left to right, right? And the first number that you find that can be converted by, what do I mean by can be converted is this, that it is profitable. That means you are able to increase this character, right, somehow. So if you are able to convert this character to a better character, then you should do this. And starting from this position, convert all the numbers that are possible, right? And just stop there. And this is your only subarray that you need to touch, right? The rest of them should be untouched. So this will be your answer. 2, 5, 5, 1, 3, sorry, is the biggest number that you can form, right? And now you also know how you're going to solve this problem, right? And you can clearly see what is the time complexity. It's linear. All you are doing is traversing the number from left to right, right? So yeah, this is how you're going to solve this problem. For this problem, let me also show you the code so that you have a better idea where it is. How do I stop this? Share. And let me just share this screen this time. So for this one, we'll also show you the code. I think yeah. So here you see, what are we doing? Nothing special. We are reading n. Oh, sorry. We are reading n and the number. Number is, I'm reading as number. I'm reading as string, right? And I have a function f. It was named g, right? I named this function f, sorry. So this is the function that does the work of mapping, right? After reading n and the number, you need to read the mapping, right? Ith digit will be mapped to this digit that you are reading from the input, right? And I'm reading the input. After that, what I'm doing, I'm going through the solution. Let me just, sorry. I'm going through the number and I'm checking if the mapping of the ith number is greater than the ith number itself. If that is, then go ahead, starting from that number, just all the number that you can change, starting from that number, which are contiguous, right? Just do that. And that's what I'm doing here in this part. And after that, after you have done, the rest of the character, the rest of the remaining character towards the towards the right should not be touched. And that's why simply break, right? Once you have changed one sub array, just break. And after that, you can print the number. As simple as that, right? So in the linear time, we are able to solve the second problem also. So this is solution of the second problem, right? So we have seen how we can solve first problem. You have seen how we can solve second problem. The third problem is actually interesting and a little bit harder, right? Because of course, this has 80 points. Previous two were only having 40 points. So clearly this one is special and is a bit hard, right? So we can proceed with this. The next. Okay. This is special. I have actually two solutions for this. I'll be explaining one solution and I'll be giving the other solution as hint. Okay, so you can try it yourself, right? So how we can proceed with this? Let's see. So there is a marathon next week, and uh, there are n athletes that are participating in this. Every athlete is from a different city, okay, and therefore there are n cities. There are n athletes. They all are from different city. So of course there are n cities, number from 1 to n. An athlete can run from one city to another city if there is a road connecting them. Make sense? Okay. Also, the length of all the roads connecting any two cities is equals to 1 unit. Okay. And so basically, what we learn here, we have n cities and we have roads, basically a graph, right? And how many roads are there? If we can get idea of that, then we can know that we can know for sure that this is a tree or not. All the athletes want to cover as much distance as possible and don't want to repeat the city for practice. Okay, so they want to cover as many cities, right? They want to cover as much distance. They want to cover as much distance as possible without repeating any city. Okay. Now, you are the coach of these athletes and you are interested in the data about how much distance they can run. Therefore, you have to determine the maximum distance an individual can cover. Okay, so we are coach. We have to find out for each city, for each athlete, that how much distance he will be able to cover. Okay, and the only constraint we have that they don't want to cover the same city more than once, right? So the input is uh, described here. The first line contains n, the number of athletes or the number of cities, right? Then okay, then there are n minus 1 lines. So we have n nodes and we have n minus 1 lines. That means n minus 1 edges. That means we are talking about tree. There is one specific condition, I should say, or specific particular property that is missing here. Uh, have they mentioned at any place that the graph is actually connected? If not, then there is a problem, right? So okay, also the length of the roads connecting them, this one, that one, please repeat the cities. Okay, they didn't mention it that the graph is actually connected, so it is not 100% sure. We are not 100% sure, but I think they forgot to mention that the graph is actually connected. But because of n minus 1 edges and nodes, you can consider that this is actually a tree, or maybe I'm missing it. Sorry. So you can read the problem yourself once and confirm. So basically, it is forming a tree. Okay, and for each node or for each city or for each athlete, you have to find what is the maximum distance he can cover. So number of cities can be as large as 2 into 10 power 5. Now, for this input, 5, 1, 2, 1, 3, 3, 4, 3, 5. Answer is 23, 23, 3. Okay. Let's go ahead and see how we'll solve this problem. Okay. So can I directly go to whiteboard? Yeah, we can. That's great. Okay. So So let me take my white. Okay. So let's start with the new page. Let's go for the solution. Okay. So basically we are given a tree. I forget how the tree was given, but let's say something like this. One is connected to 2, one is connected to 3, 3 is connected to 4, and 3 is connected to 5, right? This is the structure of the trees, right? And we know each of the edge is of length 1. For each athlete, we have to find what is the maximum distance it can cover. For example, first, second, third, fourth, fifth. One can cover at max distance 2, right? Because from here he can go to here, and from here he can go to here, or from here he can go to here and then here, right? So one can cover at max length 2 distance. Oh. Now, why he can't cover more than that? Because once you reach this, or once you reach this, you can't go back, right? So you can't track back actually. So for node 2, we can actually cover distance 3, right? I can go from here, here, and here. For node 2, we can, or athlete 2, we can cover distance 3. For athlete 3, I can either go here, or I can go here or here. If I go this path, I can cover 2 distance. If I go this path or this path, I can cover only 1 distance. Of course, the maximum I can cover is 2. Done. For node 4 and 5, it's same. They all can cover length 3. From 4, I can go here, here, and here. So length 3. Same for 5. I can go here, here, and here. So 3 again. So this is the distance. This is my nodes. Okay. Now the question is how to actually find this. One of the possible solution is this, which is worst case solution, but brute force only. For each node, starting from each node, you can simply run a DFS, right? Starting from, let's say, I want to find out what is the maximum length node 3 can cover. All I have to do is run a DFS from node 3, considering this as root, right? So from node 3, I can run a DFS and find out the maximum height of this tree, basically, right? Height of the tree is maximum distance you can cover from root to certain leaf node, right? So, for example, if I'm going to run DFS from node 3, 3 will be my new root. So the tree will look like something like this. Okay. 3 is connected to 4 and 3 is connected to 5. If you root the tree at node 3, this is how the tree looks like. And the maximum you can cover actually 2, right? And that is also height of the tree. So to solve this problem using brute force solution, what you can do, for each node, run a DFS and find out height of the tree. And that will be your solution. But how much time it's going to take? See, for a tree, DFS runs in big of n time, right? There are n nodes, right? So in total, overall time complexity will be quadratic, and that we don't want, right? Can we do better than this? Yes, we actually can. And as I told you, there are 2 different solutions. One of the solution uses dynamic programming on tree, right? So here's the thing. Dynamic programming, or DP, is a I can say quite famous concept in not just famous, it's quite hard concept in competitive programming contests. Usually DP questions appear if you have participated in any contest on code forces, especially on diff 2, if I talk about. In any contest, the problems are named as A, B, C, D, and E. You know that, right? A is the easiest one, and D or E being the hardest one, right? And usually DP problems start appearing from C onwards, depending on how hard they are, can go up to E. Usually DP problems are actually considered hard because figuring out the solution is tough, right? So what can you do for finding DP solution or getting better at DP is practice, right? There are many algorithms in DP like LIS, longest increasing subsequence, or like staircase problem, and so on and so forth. There are a lot. So learn those. And usually what happens, the problems that are there are variation of the cliche DP algorithms, right? So go ahead, learn the DP algorithms. DP algorithms themselves are quite hard. When it comes to DP on tree, it is even harder. There is also a concept on tree which helps you answer queries, that is rerouting DP, right? So there is DP on tree, right? You need to learn this rerouting DP. This is also part of DP on tree. I'm mentioning it separately because I believe it actually, let me just rerouting DP. Okay. Okay. So I'm giving it an extra recognition because this is one of my favorite concepts beside binary search, believe me. So pay special attention on these two. Of course, if you are going to learn DP, you have to go through all of this, right? You have to learn this, you have to learn rerouting DP, you have to learn digit DP, also quite hard concept, and bit masking DP. There are a lot, right? So go ahead, learn all of those algorithms. So what we are going to do, we are going to use DP on tree and find solution of this problem. How? Let's see. The solution will be in having time complexity linear. So let's build a tree. Previous tree itself, 1, 2, 3, 4, and 5, right? So what I can do in here, you have to calculate two things: DP1 array, okay, and DP2 array. And also you need to keep track of something which is the child node, another array. Now what is this? See, first of all, DP1 will tell you the maximum path, maximum distance from the current node that you can travel, okay? And this is the second maximum distance that you can travel, right? So let's go ahead and build this array. So starting from node 1, what you'll do, you'll make a DFS call to node 1 and try to build these two, okay? So what you do, you start from here. Node 1 is at distance 0, right? So of course, initially, all of the values are 0. I don't have to change anything here. So from here, let's say you made a DFS call to node 2, right? You reach node 2, it's DP1 and DP2. Sorry, when I reach node 1, I initialize its DP1 and DP2 to 0. At this point, I haven't found any path, right? When I reach certain node, I reach node 2, I'll initialize its DP1 and DP2 to 0, 0, right? And now from here, there's nothing to explore from node 1, so I'll return back. So when I came back, node 1 will try to maximize its DP, right? Now, for node 2, it's DP1 for node 2 is actually 0. That means the maximum path you can cover from node 2 in its subtree. At this point, we are only considering subtrees. Inside of which maximum you can cover is 0, right? Inside subtree of node 2, right? There is nothing. So 0 plus 1 is 0 plus 1, that is DP1 of node 2 plus 1 greater than current DP1 of node 1. The answer is yes. So I'll change it, right? So let me take eraser, delete it, go back to drawer. This will become 1. How? I can take the maximum path of this and then add this edge, right? And that will be maximum path. That can be maximum path of node 1. Maximum path of node 2 was only 0. Add this one plus 1. So maximum path that I found for node 1 is of length 1. Done, right? So now node 1 will make a DFS call to node 3. Initialize its DPs 1 and DP2 to 0, 0. From there, let's say you made a DFS call to node 5. Let's go to node 4 first, right? Because otherwise I need to write, write blank spaces. So I'm at node 4 again, DP1, DP2, initialize with 0, 0. From here, there's nothing to explore. I'll go back, right? I'm going back to node 3. Node 3 will check, hey, node 4 just came back, right? And is the maximum path of node 4 plus 1 greater than my maximum? The answer is yes. Maximum of node 3 is actually 0. And 0 plus 1, 1, 1 is greater than 0. So what you will do for node 3, its maximum path found till now will become 1, right? You see, we are not calculating DP2 because at this point, there's nothing being changed here. I'll show you in a moment. That will change just now. Now, work of node 4 is completed. So node 3 will make a DFS call to node 5. Node 5 will initialize its DP1, DP2 to 0, 0. And from here, there's nothing to explore. So we'll go back to node 3. Node 3 will say, hey, is maximum path of node 5 plus 1 greater than my maxima? The answer is no. But is it greater than my second maxima? The answer is yes. So second maxima will be updated to 1, right? So second maxima of node 2, node 3 will be updated to 1. You see, now second is being changed. So the work of node 3 is completed. So it will go back here for node 1. We are at node 1, right? Node 1 will check whether maximum path of node 3 plus 1 greater than my maximum. The answer is yes. Maximum path of node 3 is 1. 1 plus 1 is 2. 2 is definitely greater than 1, right? So at this place, I'll have to, but have a look at this. Since we are updating this, make sure that this maxima is transferred to this maxima. Whatever was your first maxima, if you are adding a bigger number, that will become your second maxima, right? Makes sense? So, makes sense. So this will be transferred here, and here you will save 2, right? So let's remove this and this. So here I'll have 2, here I'll have 1, right? Oh my God, I forgot to add the child nodes actually. These nodes. So what happened? Let's track back again. So from node 1, I went to node 2. From node 2, I went to node 1 back. And at this point, DP1 was updated by DP2, right? Sorry, DP1 of node 1 was updated because of this node, right? So since this was the child which was providing the DP1, the maximum path to node 1, it would have been that child, okay? Then we went to node 3, node 4. There is nothing for node 4. So node 4, this is DP, child of node 2, child of node 3, child of node 4, child of node 5. For node 4, there is nothing who is providing maximum path. So for child of node 4 will be nothing. We went to node 3. And when we went back to node 3, what we did, node 4 was able to update node 3's first maxima, right? So the maximum path, so basically the child which is providing maxima to node 3 is 4. So for node 3, we'll update 4 here. So basically this tells, okay, this subtree contains the maximum path for node 3, okay? So for node 3, because node 3 is having 2 nodes as its child, which child is providing the maxima? Node 4 is providing. So that information is saved here, okay, in C array. We went to 5. 5 will have nothing. There is no child of it, right? We'll go back. 5 was not able to update DP1. So this will not change. Okay. Only those nodes which are able to update DP1 of certain node will be added here. So node 3, we went back, right? And node 3 was able to update DP1 of node 1, right? And that's why for node 1, this will change from 3 to 1. Okay. Sorry, from what was here earlier, from node 2, it will change to node 3 because now node 3 is providing the better path, right? So for node 1, node 3 is a child which is having maximum path. You can see here, right? This subtree contains the maximum path for node 1. For the rest of them, which we have not filled, they don't have subtree, you can assume, okay? For node 3, the maximum path is coming from subtree, which is having node 4, right? As simple as that. So this tells you maximum path child. This tells you the second maximum of certain node. This tells you the first maximum of certain node. But here you see clearly this is not our answer, right? Because the maximum path can not only exist in your subtree, but can exist outside your subtree. For example, node 3 is having maximum length 1 in its subtree, right? This. But the maximum path that you can travel from node 3 is actually of length 2, right? Which is outside your subtree. And that is why we need to make another DFS call that will make, at this point, you can say you have only done the pre-processing. Now you would make another DFS call, which will help each node find their actual maximum length that they can travel calculate. Okay, and how do we do that? See, either the maximum path contains in your subtree or outside your subtree. If the maximum path is outside your subtree, that means maximum that information will be there in your parents path, right? In your parents, right? Either this will be your parents first maxima or the second maxima, right? See, one, see, let's say for node 4 does not have any child, right? So in its subtree, the maximum length it can cover is 0, right? We can directly see that node 4 is max in its subtree, maximum length that it can cover is 0, right? What about the outside subtree? For outside subtree, if you see, node 3 can cover maximum distance 2, right? And this will ask, hey, node 4 will ask its parent, what is the maximum path that you can cover? It will say, hey, I can cover length 2 distance, right? When we reach 4, 3 would have been actually calculated its maximum path. Okay, so 4 will ask, what is the maximum path you can cover? It will say, hey, I can cover 2. So this will ask, does that path goes through me? The answer is no, that path doesn't go through 4. So what it can do, it can take that path, add 1 to it, and that will become maxima 4, right? This will be much more clear if I explain this with, again, using an example. So let's just remove all of this and let's actually build the solution. So till now, what we have found, the maximum path in their subtree. Now let's explore outside the subtree. What is this? 0 and 1. I need to delete that also. Now you see, I'll start from node 1. Okay, this is my second DFS. The first DFS only finds maximum path in their subtree. And this you can easily implement using DFS knowledge, right? Normal DFS knowledge. Now, I'll start from here. I reach here, okay? And now, from here, what I'll do, I'll go to my child, any of the child, which is node 2. So I'll check first, is this the one which is providing me the maxima? Is node 2 the one, node 2 the one which is providing node 1 the maxima? If you see here, node 3 is providing maxima to node 1, not node 2. So node 2 is not that child, which means the maximum path that we have found for node 1 actually can help find node 2 its maxima. How? See, that path node 2 can traverse. How? We already have that path. To traverse that path, node 2, all it has to do, go from here to here and then take that path, right? So this path can help find node 2 a better path. So what we have to do, node 1 will see that node 2 is not in its, node 2 is not the child which is providing it the maxima. So what it can do, it can take its first maxima, which is 2 plus 1 because of this edge, and this can help node to maximize its maximum distance that it can cover, right? So 3 is clearly greater than 0, right? So I'll add 3 here. I'll add 3 here, right? I'm come here. So we are now at, after doing that, after updating the distance, what we'll do, we'll make DFS call to node 2 and say, hey, just update, let all your child nodes know that you have a path of this length if they were in case they want to update it, right? Node 2 at this point have no child nodes, so it won't be able to help any of them, right? So it will track back. We are back on node 1. So node 1 goes to, node 1 makes to before making a DFS call to node 3, it will check whether I'll be able to help node 3 or not. For that, what it can do, it can check who is node 3 my the child which is providing me the max path. Yes, node 3 is the child which is providing node 1 its max path, right? So that path cannot be given node 3 to extend its max path, right? The path basically covers this, right? And I can't say, hey, node 3, I have a path of length 2, just traverse this and go through that path. In that case, what will happen? You will go here and then here. The path becomes of length 3, but in that case, you are traversing node 3 2 times, right? And that is not the correct path. So if node 3 itself belongs on the path which is maximum, that path cannot help node 3 maximize its path, right? So that is the reason why we have DP2. So node 1 says, hey, the path, the maximum path that I have, that can't help you because you already lie on that path, right? So instead of that, you can try to use my second maxima. That surely won't go through node 3, right? So second maxima of node 1 is 1. So you see, 1 plus 1 is actually 2, and 2 is greater than 1, right? 2 is greater than 1. So what we can do, we can replace 1 with actually 2, right? And this time for node 3, maxima comes from node 1. So this will also update, right? So let's do that. So first of all, maxima, max length that we can cover will become 2, right? 1 plus 1, 2. So max length that node 3 can cover becomes 2. And also this time the node which is providing the maximum path is actually node 1, right? So this will also update. Whenever you are updating DP1, you have to update the child. In this case, we can't even call this child, right? You have to update the node which is actually providing you the maximum path, and node 1 is actually providing that maximum path, so you will update that as well. Now, since node 1 has helped node 3 find the best path, right? It will make a DFS call to node 3 and will say, hey, I've done my part, you do your, and let your child nodes find a better path, right? So we are at node 3. What we'll do, uh, the first node in the adjacency list, or basically we have node 4, right? This will traverse, but before making DFS call to node 4, what we'll do, we'll try to maximize path for node 4. What we can do, we'll see whether node 4 is the one which is providing max path for node 3. No, node 4 is not the one. So I can provide max path, which is of length 2 for node 3 plus 1. That will be new maxima for node 4, right? So new maxima for node 4 instead of 0 will become 3, right? Instead of 0, it will become 3. And also we can update the which node is providing the maxima. Node 3 is providing maxima to node 4, and the new maxima is 3 actually, right? You see, we are not transferring first maxima to second maxima because that was already 0, right? Again, after helping node 4, we'll make a DFS call to node 4 so that it can help its children. There are no such children, so we'll come back to node 3. Node 3 has one more child, 5, so it will try to maximize its path also, right? So node 3 will check whether node 5 is the child, is the node which is providing maximum path to node 3. The answer is no. Node 3 is being provided maximum path through node 1, so that means DP1 of node 3 can help node 5 find its maxima. DP1 of node 3 is again 2. 2 plus 1 is 3. So for node 5, first maxima can become 3, right? So let's update first maxima as well as the node. Node will become 3. 3 is providing the maxima, and the maxima is 3 itself, right? After that, it will make a DFS call to node 5 to say, hey, just help your child do that. Node 5 doesn't is a leaf node, so don't have any child. So we'll go back to node 3, right? Node 3 doesn't have any child to reduce their, or basically maximize their length. So we'll go back to node 1. Node 1 doesn't have any child to maximize their length, so we'll go back to main function from where we have made a DFS call to node 1, right? After that, if you see, this is your solution, right? 2, 3, 2, 3, 3 was our solution, right? So we made 2 DFS call. Sorry, we made 2 DFS call. First DFS call will find all the max for each node maximum path in its subtree, right? Basically height of their subtree. The second DFS, let's call this DFS1. Let's call this DFS1. Now your DFS2 will actually help you find the maximum length, which is outside your, basically outside your subtree, because maximum length, maximum path doesn't need to be inside your subtree. It can be outside your subtree, right? So after you have done first and second DFS using the DP on tree, we are able to do this in 2 DFS, right? And each DFS takes big O of n time. So you can solve this problem in big O of 2n. And since we are talking asymptotically, you can drop the constant and the overall time complexity becomes linear, right? We have found a much better solution. How much time we have? We have a lot of time. Now, Casey, so you got the idea, right? How you are going to solve this solution. I can also show you the code. Should I? Let me take you to the code first, and then I'll give you a challenge, also a hint how you can solve the same problem in a different way without using DP, right? That method also takes apparently, I mean, by chance, that algorithm also uses two DFSs to find the exact same solution. Okay, but that doesn't use DP. Yeah, we only maximize the distance array, and that doesn't utilize DP, right? So let me show you the code for it first. Okay, so let's stop the share and go to the code. Okay, so this was the problem. Yeah, this is the problem. So let's have a look at solution. So go to C++, and here you see. So you see, we have D1 array and D2 array. D1 and D2, yeah, distance 1 and distance 2, right? I name them DP1, DP2, right? And this is your C array. So here you see, this is DFS1. Let me show you from the main function. What you did, you're taking input n and then reading n minus 1 edges. After you have prepared your tree, what you are doing, you are making call to DFS and DFS2, basically DFS1 and DFS2, right? Making call to node 1 only, right? Each time. And minus 1 is actually parent. Okay. Now, in the first DFS, you remember, you set DP1, DP2 to 0. After that, you go through the adjacency list of the current node. And each time, what you do, first you make DFS call so that they can also calculate the distance, height, basically, in their subtree, right? After that, you check whether this has a maximum path or not. So using this, can I find maximum path? For that, if dp1 of x plus 1 is greater than dp1 of current node, so dp1 of current node will be updated, right? dp1 of current node is dp distance, basically dp1 of child node plus 1, right? But before that, we transfer the first maxima now becomes the second maxima. That's why dp2 of v is equals to dp1 of v. Basically, we are transferring first maxima to the second maxima. After that, we are updating the first maxima, and we are also setting which node providing me the maximum path, right? And if that is not the case, I'll check whether at least this is providing me better second maxima. In that case, I only need to update second maxima. And when you update the second maxima, you don't update the child, right? The node which is providing you the maximum, right? You don't update that. So it is easy to understand, right? In the second, what we were doing, we were not setting dp1, dp2 to 0. We only came there to provide better result for child nodes, right? So in the adjacency list of current node, you will check whether x represents the child node and v represents the current node, right? So for each child node, you're checking whether its dp1 is actually smaller than dp1 plus 1. Yeah, again, we need to take care of the fact that whether the child that we are going to process is the one which is providing me the max path, right? If it is providing me the max path, then all I can do, I can use my dp2 only, right? Because dp1 already contains x, I can't use that. So if basically dp2 plus 1 is greater than the dp1 of x, then what you can do, you can perform the exact same thing that we do. Because we are calculating the first maxima will be transferred to the second maxima, and of course you will update the node, right, which is providing you the first maxima. Otherwise, if that is not the case, you can always update the second maxima. If it is not the child that is providing you the maximum, if this is not the node that is providing you the maximum path, right, that means you can directly use your first maxima, right? So first maxima of the child node becomes first maxima of the parent node plus 1, and before you do that, you transfer first maxima to the second maxima, right? And also you update the child. After that, you make a DFS call, of course DFS2, right, to the child node, so that they can help their child nodes find a better solution. So you see, only 2 DFS and you found your solution, and this is your DP on tree, right? You see, linear time solution. Now that we have this, I told you that this problem can be solved. This problem can be solved in one more way, right? And I have tested the solution that works actually. We can also prove that. The same you can do, right, using 2 DFS without using DP on tree. How? for you, hint is use, what do we call it? Diameter. Okay. Diameter of tree. Why I'm telling you this? Because using this way, you are going to learn one extra algorithm, right? Now I've given you an extra work. Go ahead and learn diameter of tree. Okay. Using diameter of tree, you can also find out solution of this problem. And how you find diameter of tree? To find diameter of tree, you make two DFS call, right? Let me tell you myself. Pick in first DFS, pick any node, let's say node 1, and find the node which is at the which is farthest from node 1, right? You can find node 5, right? You have found it. In DFS1, pick any arbitrary node, doesn't matter which node it is, and find the node which is farthest from that node. 5 and 4 both are, let's say we picked 5, right? So now we have 5. Now run a DFS from node 5 this time. Okay. Now when you found 5, this represents one end of a diameter. I forgot to mention what is a diameter. So diameter is the maximum length between any two nodes in a tree. Okay. I'm talking about diameter of a tree. Diameter is the maximum length, maximum length of a path that you can find in a tree. Okay. Now, the maximum path you can find is actually 3, right? So that is diameter, and you have to find two endpoints of it. One of the endpoints is 5, right? Which we can find using first DFS. Now make a DFS call from that node, one of the endpoint, and find again the farthest node. That will be 2, right? So these two are the endpoints of your diameter. You see, this is not unique. 4 and 2 could have also been the endpoints of the diameter, right? So endpoints of diameter are not unique, right? Once you have found the diameter, you can actually find the maximum distance a node can cover using these two only, right? I think I should leave this as a homework for you guys to do. Okay, so go ahead, learn how you find out down. I already told you, but still learn in deeper detail that how you can actually find out diameter of a tree, right? After that, just think how you can actually find out what is the maximum distance a node can cover, right? Using in a tree, using diameter of a tree, right? Using these two nodes. So this I'm leaving you as homework for you guys. Okay. So we have covered like 3 problems, I guess. New share, screen. Uh, my voice may be feeling a little heavy because I'm having cold. Okay, so this, come on, we have solved 3 problems. Okay, should we take any questions, if, or should I continue? Vedankur, if you are present there, should we take any questions, or should I continue with the 4th and 5th solution? Okay, so I think Vedankur is taking a little bit of rest. I can understand that. So let's proceed with the 4th solution. Should I proceed? Let me ask myself, should I proceed this? I mean, with this, or should we take a 2-minute rest? Okay. Okay, so give me 2 minutes of rest. Okay, it's like 8:10. Let's proceed. Let's go continue this at 8:12. Okay, I'm giving like 2 minutes rest to myself. Sorry, I just need water. I'm not sure if the video is being, I mean, my face is being live streamed or not. Okay, 1 minute passed. We'll only take 1 more minute, and then we'll continue, right? Oh, Okay, just okay. So it's 8:12, and let's continue with the next problem, which is, I think this is, yeah, this is also almost medium level question, I guess, 80 of 80 marks. So let's see. The problem says that, let me read the problem. That let's put my pen tab aside. Okay, so we have ninja stuck with a problem on strings. Happens with me a lot of time. The problem is to maximize the number of following operation on a given binary string. Okay, so the string we have provided is actually binary. That means each character will either be 0 or 1. The operation is made of the following two moves. We have two moves, right? First, choose any integer j between I and the length of the string. Okay, and then the size of the string is reduced by 1. What does that mean is that in a given string, choose an integer, right? Any integer, and basically choose a position and remove that character. Of course, the string length will be reduced by 1, right? After that, what you can do, uh, after performing the above operation, first operation you perform, right? Second operation will kick in automatically, right? So first operation you perform, second operation kicks in automatically. What is the second operation? After above move is After above move, if the string is not empty, when the string is empty, of course we'll stop. Otherwise, if the string is not empty, you need to delete the maximum length of the prefix consisting of the same character. Basically, take the prefix in which all of the elements are same and remove it. Okay. And of course, again, size of the string will reduce, right? Now, in order of both move can't be changed. That means first move one will be performed and then only second moves kick in, right? We can't do like, let's perform second operation first and then go for the first operation. No. So in one operation, these two things happen, right? What is the maximum number of operation you can perform on a given string? So we have to select j in such a way that maximizes total number of operations, right? So let me give you an example so you'll understand. Let's say we had 100. Okay, and you said, okay, let's remove the first character first. As first operation, what you did is you remove the first character. Now you'll be left with 00, right? And the second operation will kick in automatically. And the prefix, you see, the prefix is actually the whole string of equal character, and this will remove all of the character. So in one operation, the whole string is deleted. One character you deleted, and the remaining character was removed by this, right? So in one operation, the whole string got deleted. If I go this way, I can perform one operation, right? Now let's go another way. I choose second character and I removed second 0, right? I mean, I choose this character and I remove the middle 0. Now I'll be left with 10. Now the prefix which is having equal character is only this, the first one. So this will be removed, right? In one operation, after performing one operation, I still have one character left. In the second operation, I can choose this and remove it, right? So in this way, I'm able to perform two operations, right? So it matters what character you choose to remove, right? That way, it can the total number of operations can vary, right? And we have to optimize. We have to select position j optimally in such a way that the total number of operations are maximized, right? So the length of the string can be 2 into 10 to the power 5, and there can be a thousand number of test cases. Basically, they are assuming they want us to provide a linear time solution, right? Because 10 to the power 5 times 10 to the power 3 is 10 to the power 8, right? So when n is 10 to the power 8, you can't even go n log n, right? You will get TLE. So three test cases. In first test case, you are given a string of length 6. Second test case, you are given a string of length 2, so on and so forth, right? So you will be given T, number of test case. After that, in each test case, you will be given N and the string, right? Now let's see how you are going to solve this problem. Okay. So let me grab my pen tab again. Okay. Let's solve this. here. Okay, so now let's have a string. Okay, this is the string, right? So now, since, see, first of all, your question should be, when you are processing the string, should I remove the characters which are, should I basically just transform the string in such a way? Since we only care about the prefixes, right? I mean, in the prefix, whatever equal elements it will find, it will delete that, right? So what we can do is prepare basically combine or form substrings of the string, right? In such a way that all of them are having equal elements. So I have a substring of length 2, then of length 1, then of length 1, then of length 1, then of length 2. It is optimal to process the string in left to right manner, right? First of all, you should remove the character from a substring which is having size greater than 1. This is one of the observation. Why is that so? See here. Currently, I'm having 2 to 4 and 3, 7 number of characters, right? I try to do this. Let's say I said, hey, let's remove this character, right? If you do that, what will happen? If you remove the first character, I mean the third character, what will happen? 111 will be formed, right? And if you do that, this forms a substring, right? The prefix is of length 3 with equal element, then the second operation will kick in automatically and will remove these 3 characters, right? And after just one operation, you are left with 3 elements, 3 characters, right? Initially, we started with 7 elements, and now just after performing one operation, I'm left with 3 characters, right? This is not very optimal, right? Instead of that, what you should do, you should try to remove character from a substrings which are having equal element, and of course which are having more than one element, right? And you should always process from left to right. Why? Again, take the same example. I can remove this character, right? But again, there are 2 characters and both of them will be removed. So in one operation, 1 and 2, 3 characters are removed. Instead of removing this, if I would have removed this, right, the prefix forms this element and the second operation will remove this only. So I would have removed only 2 characters and would have been left with 5 characters, right? So observation 1, remove character from substring which are having more than one element, right? So each substring, what you can do, you can actually take the input, convert them into substring array, right? What do I mean by substring array is this? Take the substring which are having equal element and then take the size of it. For example, this is having 2 elements, this is having 1 element, this substring is having 1 element, this substring is having 1 element, this substring is having 2 elements, right? Convert them into substring array, right? And then process this. Sorry, this is 1, because it doesn't matter whether there is 1 or 2. We only care about prefixes of equal of equal character, and here you have, right? So just convert this string to this array. After that, observation 1, you already know. Always remove character from a substring which is having more than one equal element. So you should either remove from here or here, right? Otherwise, if you remove this, this and this will be joined together, and that should not happen. So either remove this or this. So which one should I remove first? We should always process from left to right. That example I just showed you, right? So let's go ahead and see how many operations can be performed. So initially the string is this 1101011. Okay. So how am I going to solve this? Is this? I know this substring is having more than one element, so I'm going to reduce its size by 1, right? So this will become 1, right? Which basically means I have removed 1 character from here, right? And after one operation, I remove this character and the second operation will remove this character. So I'm left with 0, 1, 0, 1, 1, right? Now, let's keep 2 pointers, right? I and J, right? I and J, J will only point to those substring which are having size more than 1. Okay. And I will point to the current element that will be removed itself, right, by itself by first operation, second operation, because second operation kicks in itself, right? So I will be pointing to those elements which will be removed by second operation. So initially, when this was 2, right, I and j were both pointing to this. Why? Because second operation will remove this element itself. So that's why I will be pointing to this, and j always points to those substring which are having size more than 1, right? So before going to perform an operation, I'll check whether j is pointing to the current element or not. So currently its size is 2, so j is pointing to the current element, correct element, so I can proceed further. What I'll do, I'll decrease its size, basically remove one element from that substring, right? I did that, its size become 1, right? After that, what will happen is that as soon basically when the size becomes 1, first operation you perform. Now it's time to perform the second operation, right? For second operation, what you will do, whatever is being pointed by I, the whole thing will get deleted, right? So basically this element will get deleted, and that means I will increment, right? If I increments, let me just delete it. If I increments, j will also increment if j is before, j is left behind I, right? So j was pointing here. Now I will increment, right? Basically I is pointing here. Now after one operation, I'm left with this substring. Now next thing what happens? Before going to perform second operation, what we do, we check whether j is pointing to the current position or not. No, j is not pointing to correct element, right? So what we'll do, we'll keep incrementing j till it points to correct element, right? So j increment, j comes here. Is this having greater than 1? No. J will come here. Is this having greater than 1? No. J will come here. Is this having greater than 1? No. J will come here. Yes, this is having size greater than 1. So j will point there, right? So remove j from here, appoint j here, right? Now we'll go ahead and perform this first operation. First of operation means remove, decrease the size pointed by j by 1, right? So this is 2, this will become 1. So let's do this. This becomes 1, right? After this, of course, this basically means either you have deleted this element or this element, doesn't matter, right? So now after this, what happens? I increments I plus plus. So I will point here, right? Now I increments, I will go here. Basically, this is deleted, right? So this is deleted. I is pointing here now. So this character deleted, this character is deleted. So after second operation, my string will look like 101, right? And you can clearly see 101. I is pointing here, j is pointing here. Now, can I perform third operation? Before doing that, what I'll do, I'll check whether j is pointing to the correct position. No, j is not pointing to the correct position. So I'll try. I'll increment j. Now j goes outside the bound, right? J goes beyond the string size. As soon as that happens, we should stop, right? Because all of the string that are left are of the form 11111, right? 1111 means this is your substring array, right? If in the substring array you are left with 11111, that means you are having alternate equal character, alternate characters, right? So 1 2 3 4 5 6, 1 2 3 4 5 6, this is not there, right? When you are left with this, all you have to do is remove one character, other will be removed by second operation itself. Remove one character, other operation will, other character will be removed by the second operation. Basically, if there are n characters left, n by 2 number of operations will be there, seal of n by 2. So basically 5 characters are there, 5 by 2 will be 3 operations will be performed. How? Like this one, 1 2 3 4 5, right? You remove one character, one will be removed by itself, right? So one operation, again one operation, and last one you remove, there is nothing to be removed, but this still counts as operation, right? So how many since j goes outside of bound, you will stop, and now you'll see how many characters are left. How many characters are left? You can find that by finding out n minus I, right? I was pointing to 0 1 2, right? And the total number of characters for 5. Sorry, you can basically, of course, find out by position of I how many characters are left, right? So size of this array was 1 2 3 4 5, right? Size of this array was 5, and I was currently at position 0 1 2, right? So 5 minus 2 will be the remaining characters, right? Which is 3, of course. So remaining character plus 1 divide by 2. So if remaining character were even plus 1 will be odd, like remaining characters were 4. So 2 operations will be performed, right? So 4 plus 1 is 5, 5 by 2 is still 2. So 2 operations should have been performed. So we'll add 2 there. Otherwise, if this was odd plus 1 will be even, like if remaining character were 3, which is in this case, so 3 plus 1 is 4, 4 divided by 2 is 2. So 2 operations will be performed. 2 we already performed. Remaining plus 1 divided by 2 is again 2. So at max, we can perform 4 number of operations on this string. They get the idea? First of all, convert the given string into substring array, right? After that, process this. Take 2 pointers I and j. Initially, they both will be pointing to the 0th element, right? Before you go to perform that operation, what you will do, you will check whether j is pointing to the correct element or not. Till it is not pointing, just keep incrementing j. If it goes outside the bound, there is nothing. You can stop and just calculate remainder plus 1 divided by 2. That many operations you can add into your total number of operations. Otherwise, just j will be pointing to certain element from where you can delete some elements, right? After that, just decrement count of the element pointed by j and increment I, right? Just keep repeating these steps and you will find maximum number of operations that you can perform, right? And how much time will it take? Linear, because I and j are only being incremented, right? And none of them are repeating the elements, right? So this will only take linear time. Now, if I show you the code for this, let me just share again, new share. Okay. I have the code for it. Yeah, here it is. So this is, yeah. So you see what I'm doing? I'm reading, there are T test cases. In each test case, I'm reading N and ST, right? ST is the string and N is the number of characters, right? And then this is AR, this is the array, which is basically substring array that I told you about, right? And in this, I'm preparing the substring array, right? Count is equals to 1, and then checking whether ith element is equals to I minus 1th element. If so, increment count this and that, right? So this is the pre-processing part in which I'm preparing your substring array, right? After that, this is the one that finds your solution. How? Answer is equals to 0, which represents the total number of operations you can perform. Okay. Total number of maximum operation that you can perform, right? Excuse me. I is equals to 0 and j is equals to 0. I and j, the 2 pointers, both are initialized to the first element. Basically, both are pointing to the first element, right? Now, I told you, before performing the operation, make sure that j is pointing to the correct element, right? So just keep incrementing j, right? Till it is pointing to either the correct position, right? Or it goes beyond the range. If j goes beyond the range, that means if j is equals to ar dot size, simply break, right? And after that, what you have to do is calculate ar dot size minus I plus 1 divided by 2, right? Otherwise, increment your answer because you have successfully performed one operation. Increment j, right? Increment I, and of course, here, if I is equals to j, they both were pointing to the same position. Of course, when I will increment, j will increment also, right? And that's why if they were both pointing to the same position, I and j both will increment. Otherwise, what will happen? Only I will increment, and whatever was being pointed by j, its value will decrement by 1, right? As simple as that, right? And finally, you will have your answer and you will print it. So this is how you are going to solve this problem. What was this problem? I don't know the problem name, but this problem where you have to perform 2 different operations, right? And now sorry, just a question. Vedankur, are you there? Okay, let's
Hello,
me.
hello. Am I audible?
Yeah, Vedankur, you're audible. So
Uh,
we had to provide information to the students about, I guess, a Black Friday, something. Yeah,
Yes,
Black
yes. So
Friday offer.
we have a Black Friday sale, which is live
Yes.
tonight. So student can, we have 40% discount on all our courses. Plus, you can
Yeah.
get extra 20% discount if you use a
Oh,
code, which is, you can see in this poster, which is Black Friday. I'll share in the
oh,
YouTube chat box also, right?
great. Yeah.
I'm sharing it. So you can use this uh, coupon code for the extra 20%.
Mm. So in total, they'll be getting like 60% off.
So
If
it's up to 60% you can say, but yeah,
yeah,
40% plus extra 20%.
extra 20%. Yeah, got it, got it. Okay, that's a great offer. If you want to subscribe to any course, and this is applicable to all the courses provided by Coding Ninjas.
Yes, yes. So it'll
Yes,
so
that's great.
40% discount is auto applicable on our website.
Yeah,
Someone go and explore our courses, so you can
yeah,
see that 40% off. And this is live till tonight only because that's the Black Friday theme.
yeah, got it. So go ahead if you want to get subscribed to any course on Coding Ninjas. Of course, this is the time, right? So now we have gone through the fourth problem also, and we are almost done with our time limit, unfortunately. And the last problem that I have, sorry, thank you, Vedankur, for that helpful information. So now the last question that we have is actually the hardest problem that I chose was of 120 score. Okay. Now for the hardest problem, we are left with the least time, right? Like hardly I can take like 10 to 15 minutes here. So unfortunately, I cannot cover this problem completely, but let me give you some idea. So let me just explain the problem first, and then the problem statement is quite clear. Usually what happens in competitive programming, and many times I've seen, when the problem statement is quite easy to understand, the solution is just that hard to come up with. Okay, so let's go ahead with this. Yeah, just one more hint. I mean, not hint, advice from someone who has been doing competitive programming for a long time. So if you really want to get better at competitive programming, first thing I told you that go ahead and learn algorithm and data structure, right? That is the thing. Yeah, you should do that. Without that, you won't be able to go anywhere. Believe me, you won't be able to. You'll just, even if you are reading the editorial after contest ends, right? You have editorials like Code Forces provides editorial in written form, right? So when you have editorial, you read that, you won't be able to understand if the algorithm or data structure or the technique being used in that editorial if you haven't learned that, right? So of course it makes sense that you will be learning the algorithm, data structure, and techniques, right? That is must. You can't skip that. The second thing is everyone, even any person you'll ask, how can I get better at competitive programming? They'll tell you one thing. First, I mean, that is must, what I told you earlier. But the most important thing along with that is practice, right? If you don't practice, of course, you won't be able to, the chances that you will be able to solve a problem is quite less. I mean, it increases day by day the more you practice, right? What I'm telling you is this, what happens when someone has learned binary search, and if a guy just have learned binary search and you give that guy the first question, most probably he won't be able to solve this problem. And there's one more problem on Swatch. Just try it yourself. See if you are able to solve this problem. That is also based on binary search. It's a beautiful problem named aggressive cows. You'll Google it and you'll find this problem. Okay. So just because you have learned certain algorithm doesn't mean you will be able to solve the problem related to that algorithm, right? To increase the chances of this, to get better and to increase the chances that I will be able to solve a problem related to this algorithm, you have to practice. Now, how you'll practice? You can't just go there, pick a random problem and start solving it. No, that is the worst. way you can practice. The better way is by learning some algorithm and then search for problems that are related to it. Okay, related to that algorithm. First thing. Second, always solve a problem which is a little outside of your comfort zone. If you see a problem and you are like, hey, I know how you can solve this problem. I literally can code this problem. Give me 10 minutes. Don't do that. That will only waste 10 minutes of yours. That is not going to teach you anything. So don't go ahead, right? Solve a problem which is just little outside of your comfort zone. When you look at the problem and you're like, maybe I can apply LIS there, but memory constraint is higher because if I apply LIS, I require n square space, this and that. You are almost able to find the solution of it, and that looks like you will be able to solve the problem. I know sometimes happen that some problems look like you will be able to solve a problem and you are not able to solve that problem. It happens, understandable, completely understandable. But still, most of the time when you think that maybe I can solve this problem, I just need certain hints, go ahead with that problem. Those hints that you need now, those are the things that will teach you and make you better. Okay, next time you won't need those hints. You'll only have an idea, hey, I solved this problem, I was stuck in this problem, and then I went with this hint, and then using this I was able to optimize the overall solution. So always practice problems which are a little outside of your comfort zone. Okay, and it is not just me. Many experienced programmers that you will ask, they'll always give you this exact answer. Okay, enough that talk. Let's come back to the problem. So the problem, Ninja is a fifth problem, which is the hardest, 120 points. Okay, Ninja is a student who loves mathematics a lot. I love that too. It's not like I'm the best in this, but I love it. Even if I'm getting not even if there is a mathematics problem related to mathematical algorithm, be it number theory or geometry or something, even if I'm not able to solve that problem, I'll still love that problem as much as I would have loved that problem if I was able to solve the problem. So Ninja is a student who loves mathematics a lot. Okay. Recently, he learned about perfect squares, right? And he found it very interesting. Suddenly, he started thinking about the number whose sum of digit is a perfect square and how many numbers are present between two integers L and R, right? Now you learn something, you create a problem, you ask someone else to solve it. So see here, what happens? Ninja learns that what is a perfect square, and now he suddenly just wonders, hey, I have a range of numbers. How many numbers are there in this range such that sum of the digits of these number is actually a perfect square? Great problems. After putting in quite a lot of effort, he got tired and asked you to help him. Okay, we are here to help, right? He gave you a task, count all the numbers between L to R whose sum of digits is a perfect square, and you don't want to do it manually, of course. Why? Let me show you. L and R can be as large as 10 to the power 100. See, that means you can't even read L and R as integer, because long int, which is 64-bit integer, can take up to 19-digit number only. R can be as large as 10 to the power 100. That means it has 100 digits. You can say, okay, I can use boost library of C++. That won't going to help you either. Even boost library can have like 512 bits or 1024 bits, right? Even that has limits. Even that won't be able to solve a number which is having 100 digits. So mostly this, let me tell you, is actually a problem from DP and a hard version of it, which is known as digit DP. Okay, so how do you spot a problem which is of digit DP? Usually LNR will be huge, like 100 digits, 500 digits, 200 digits. That you'll find some problems on digit DP on Spoj. Okay, so the easiest problem you can, so before you are able to solve this problem, make sure that you understand what is DP, not DP. Of course, before learning digit DP, you need to learn DP, right? So before finding solution, before going for the solution of this problem, make sure that you know what is DP, dynamic programming, and you learn digit DP. With digit DP, solve the easiest problem there is for digit DP, and that is digit sum. Digit sum problem, is available on spot, you can find it. Okay, so first learn digit DP, then you'll be able to solve this problem. Now, digit DP, the problem that I'm telling you, find the digit sum. Here, what we have to do, in a given range, we have to find all the numbers whose digit sum is a perfect square. And digit sum that I was talking about, sum of digits problem that you can solve using, that is the easiest problem you can solve using digit DP. In that problem, you are given a range, L and R. There also range is so huge, right? In that, what you will do, they'll ask you to find sum of digits of each number in the given range, right? You can say that, hey, I can do that using a for loop, right? But again, see, this is huge. We can't do that. TL is for sure waiting there. So learn digit, first thing, learn digit DP. Solve digit sum problem using digit DP. After that, how you'll solve this problem, I'll tell you. Take the digit sum solution. In that, all you have to do is modify a little bit. When you reach end of the recursion, you will have your digit sum, right, of each number, right? Here also you have to find digit sum of each number, right? And then check whether this is a perfect square or not. So you can basically modify the solution of digit sum, right? And at the end of your, basically in the base case of your recursive solution, you will have digit sum of the number that you have made so far, and check whether the given digit sum is actually perfect square or not. If it is perfect square, return 1, telling that, hey, this is a valid number. Take its contribution into the overall sum. That's why you'll return 1, right? Otherwise, if it is not a perfect square, return 0, right? So how you'll solve this problem? You'll solve this problem using digit DP. So go ahead and learn digit DP. If I show you the solution, unfortunately, I won't be able to show you overall solution of this problem, because I have to take you through digit DP explanation, and that is huge. If you find any lecture, of course, there are lectures on coding ninjas, I know, which are teaching digit DP. I'm 100% sure that digit DP lecture can't be less than 1 hour. Can't be. I know. I have experience of that. Okay, so of course, in the remaining time, I won't be able to explain that, right? So here you see, this is the base case. This is basically end of a recursive call, and at this point you have a number in the given range, and you have its digit sum in this. If this digit sum is a perfect square is a Boolean array, right? If this is a perfect square, at this index I have saved true. In C++, true means 1, so it will return, otherwise this will return 0, right? To find a solution, how you'll do, what you can do, you'll simply find solution till R. So you will build your solution in such a way that get answer, which is DP solution, finds you all the numbers in the range 1 to R, which are having their digit sum as perfect square, right? So you get all the numbers in the range 1 to R. I don't want in the range 1 to R. I want in the range L to R, right? So what I'll do, I'll calculate all the numbers which are having their digit sum as perfect square from 1 to L also. And R minus L, I can do that, right? But you might be thinking that L should also be included in the solution, which is absolutely correct. That's why you calculate R minus L, and for L, calculate separately. If this was a perfect square, add 1, otherwise don't, right? And of course, after that, just take modulo, test by 9 plus 7, because the number can be huge, and print the solution. As simple as that, right? So with this, unfortunately, I have to say bye to all of you, and here we can stop. Now again, before I leave, here you see we have learned a lot. Starting from this, from the first problem, you learned how binary search can be used in a different way, right? Binary search is more than just finding a number in a sorted array, right? Second, what was second number? Second, we learned about this was more based on greedy algorithm, when you have to change certain digit and maximize the number, right? So this was utilization of greedy algorithm. This is, you have to learn. You have to learn binary search. You have to learn greedy algorithms. You for the last question, you have to learn not just last question, a third problem also. You have to learn DP, that is dynamic programming. Third problem, utilize dynamic programming on tree, right? And fifth problem is utilizing advanced version of it, which is digit DP. Digit DP and bit masking DP are hard DP algorithms. Okay, and in the fourth problem, we again utilized two pointer method along with greedy algorithm to overall maximize the sum, right? So you see variety in the algorithm, and that is the exact reason why most of the teachers who will teach you competitive programming, or if you ask someone suggestion who have been doing competitive programming, will tell you to go ahead and learn variety of algorithms and data structure. Not only that, practice different problems. Question 1 tells you to practice different problems of a certain algorithm, right? So with this, we can stop here, and I have to say goodbye. And thank you all for joining this session. You all have been a great audience. Thank you. Vedankur,
Yeah, yeah, Vakar.
I think we can wrap it up.
Yes, yes, we can wrap it up. And thank you, Vakar, for the
Yes,
session. And I
thank
hope
you.
the student must have got their, problems. So this webinar will be live, will be live on our YouTube platform also. So you can come back and check anytime again and see the solutions. Thank you, Vakar, and thank you, everyone. Thank you so much.